So, all right. I want to start my lecture. So this slide present the time domain simulation result for the system studied in example 1110 using Ullern numerical integration method with a small time step of 0.001 second. So the fault is applied at zero point 0.1 second, and system stability is analyzed for different fault clearing times. When the fault is clear at t is equal to 0.25 second, the system remains stable. At t is equal to 0.411 second, the rotor angle approaches the unstable limit the value of delta U, indicating critical stability. And however, when the clearing time increases slightly to 0.412 second, the rotor angle exceed the stability limit and the system losses synchronous around t is equal to 0.615 second. Let me add a student. All right. The oscillations observed in the stable case occur because the simplified model does not include damping effects or system losses. Okay, this slide illustrates the transient stability behavior of a power system in terms of the rotor angle variation delta following a fault and its subsequent clearing. Okay. The figure shows the three distinct dynamic responses: stable, marginally stable, and unstable, depending on the system ability to maintain synchronism after disturbance removal. So when the fault is clear, um, um, for example, this is a green curve, the rotor angle exhibits damped oscillations and eventually returns toward a steady operating point, indicating a stable condition. In the marginally stable case, it means a blue curve. The system operates close to the stability limit, where the rotor angle reaches a peak and slowly drifts without proper damping, highlighting a critical boundary of stability. In contrast, the unstable case curve, it means a red curve, demonstrate that if the fault is cleared too late, the rotor angle continues to increase behind the unstable equilibrium point, leading to losses of synchronism due to sustained acceleration. So, in overall, this slide emphasizes the importance of fault clearing time in determining system stability and visually demonstrates how post-fault dynamics govern whether the generator remains in synchronism or diverges into instability. Okay, this slide investigates the effect of generator loading on transient stability using time domain simulations of the system from the previous example. Euler method has been applied with a time step of 0.001 second, while the fault occurs at t is equal to zero point 0.1 second and is clear at t is equal to 0.25 second. So the results show that system stability strongly depends on the pre-fault loading level for P pre-fault is equal to 1.1 per unit. The system remains stable after this disturbance. When the loading increases to 1.385 18 per unit, the system becomes marginally stable and operating very close to the stability limit. A single further increase to 1.332 per unit cases instability, demonstrating how heavily loaded generators are more vulnerable to losing synchronism during their faults. Okay, this slide illustrates the effect of generator loading on transient stability through the variation of rotor angle delta over time under fault condition. At the onset of the fault, the electrical power output of the generator is reduced, causing the rotor angle to increase as the motion accelerates due to excess mechanical input power. When the fault is clear, the system response depends strongly on the initial loading condition and system operating point. And the green curve represents the stable case where the rotor angle oscillates but eventually settles, indicating that the generator successfully regains synchronism. The blue curve shows a marginally stable condition where the rotor angle continues to oscillate with reduced damping and approaches the stability limit. In contrast, the red curve demonstrates an unstable scenario where the rotor angle increases continuously after fault clearance, indicating losses of synchronism. So overall, the figure highlights how higher generator loading reduces stability margins and increases the likelihood of instability following the disturbances. Okay, this slide introduce the dynamics of multi-machine power systems and highlight the limitations of the single machine infinite bus assumption. In earlier studies, it was often assumed that a fault affects only one generator while the rest of the system remains unchanged. However, in practical power systems, disturbances influence all interconnected generators. Fault changes the electrical power injected into the network, so which consequently alters power flow in the transmission lines. Because generators are electrically coupled through the network, so the transient behavior of one machine affects the dynamics of the others. Therefore, accurate stability analysis requires simultaneous modeling and simulation of all machine interactions within the system, power systems. Okay, this slide presents the classical representation of a multi-machine power system containing n interconnected generators. Each generator is modeled as a constant internal voltage source behind its transient reactance, which is a commonly used assumption in transient stability studies. The generators are connected to a common transition network and load system, and each machine injects current into the network according to its internal voltage magnitude and rotor angle. So the model simplifies the complex dynamics of synchronous machines while still capturing the essential interactions among generators during disturbances. So this representation forms the basic for analyzing rotor angle stability, power transfer, and dynamic behavior in large interconnected power systems. Okay, this slide presents the mathematical model used to describe the dynamics of a multi-machine power system. For each generator, two differential equations can be defined, one for the rotor angle and another for the rotor speed. The first equation describes how the rotor angle changes relative to the synchronous speed, while the second equation represents the swing equation relating acceleration to the difference between mechanical input power and electrical output power. So in a system with n generators, the overall model consists of two n first order differential equations. And an important point here is that the electrical output power of each generator depends on not only on its own rotor angle, but also on the operating condition of the entire interconnected network. So this demonstrates the strong coupling between generators in multi-machine stability analysis. Okay, this slide explains the initialization process for determining the internal electromotive force or EMF of synchronous generators before dynamic or transient stability studies are carried out. The first step is to perform a power flow analysis in order to obtain the operating conditions of the network, including bus voltages, active power, and reactive power injections. For generator I connected to bus K, the complex power injection is represented as SI is equal to PT plus JQI, where PI is the active power and QI is the reactive power supplied by the generator. So next, the bus voltage is expressed in polar form as VK is equal to VK with an angle of delta K, where VK is the voltage magnitude and delta K is the voltage angle obtained from the load flow solution. So using the complex power equation, the generator current can then be calculated. So the stator current of the generator is given by this equation. IA is equal to SA over VK conjugate value, which simplifies to this equation. This equation relates the electrical power injection to the current following from the generator into the network. Finally, the internal transient EMF of the generator can be determined using the generator transient reactance X prime I. The internal voltage can be expressed as EI prime is equal to EI prime with delta I, which is equal to VK plus J XI prime II. So physically, this means that the internal EMF can be obtained by adding the voltage drop across the transient reactance to the terminal bus voltage. The diagram on the right hand side here illustrate this equivalent circuit where the generator internal voltage source is connected to the network bus through the transient reactance JXI prime. So this initialization process provides the starting conditions required for accurate dynamic simulation of generator behavior in power systems. Okay, this slide describes how loads are represented as equivalent admittances during the initialization stage of power system dynamic studies. Instead of modeling loads directly as constant power elements, they are converted into admittance form to simplify network calculations and enable easier incorporation into the bus admittance matrix. So the load connected at bus L is represented by the complex power demand. SL is equal to PL plus JQL, where PL is the active power consumed by the load and QL is the reactive power demand. The voltage at bus L, um, denoted by VL, which can be obtained from the power flow solution, Using the relationship between complex power, voltage, and current, the load current also can be determined. Let me add a new student. The load admittance is then calculated as the ratio of current to voltage. This results in the equivalent admittance expression, YL is equal to JL plus JBL, where GL represent the conductance and BL represent the susceptance of the load. And by substituting the complex power relationship into this equation, the admittance can be expressed as this equation. So this equation shows that the equivalent load admittance depends on both the active and reactive power demand as well as the square of the bus voltage magnitude. So modeling loads in this way allows them to be directly incorporated into the network admittance matrix, which is particularly useful for transient stability and dynamic simulations because it simplifies the numerical solution of the system equations. So this slide describes the construction of the admittance matrix used in power system dynamic analysis. Each generator is modeled by its internal transient voltage E1 prime with a delta 1 behind the transient reactance of X1 prime. The internal generator buses are numbered from 1 to n. You can see this is 1 to n buses, generators, while the remaining network and load buses are numbered from n plus 1 to n plus m. So current injection exists only at the internal generator buses because loads are already represented as the admittances within the network. So using this arrangement, the system equations are written in matrix form using the uh, uh, partitioned admittance matrix Y. So this formulation connects generator internal voltages, bus voltages, and injected currents and forms the basis for transient stability and dynamic simulations of power systems. Okay, this slide presents the initialization step for building the network admittance matrix used in power system dynamic analysis. The relationship between generator currents, internal electromotive forces, and bus voltages is represented in matrix form through the partition admittance matrix. So in this formulation, the vector E represents the internal EMF of the generators, where the voltage magnitudes are assumed constant, while the rotor angle delta I vary dynamically during system operation. So the vector V contains the voltages of the remaining buses in the network, and the vector I denotes the current injected by the generator. So the admittance matrix is divided into four submatrices: Y and N, Y and M, and YMM, and YMM. So which describe the electrical coupling between generator buses and non-generator buses. So this matrix-based representation forms the foundation for network reduction, stability studies, and transient analysis in modern power systems, enabling efficient modeling of generator interactions and system behavior under disturbances. Okay, this slide explains the reduction of the power system network to obtain a simplified model focused on generator dynamics, particularly the rotor angle delta. Since transient stability studies are mainly concerned with the angle behavior of synchronous generators, the remaining network buses and load buses can be mathematically eliminated from the system equations, starting from the admittance matrix formulation. The current injection equation is divided into generator and non-generator bus generator components. So by setting the injected current at non-generator buses to zero, the bus voltage vector V can be expressed in terms of the generator internal voltage vector E. Substituting this relationship back into the generator current equations produces a reduced admittance matrix Y, which directly relate the generator currents to the internal generator voltages. And this reduced system significantly decreases computational complexity while preserving the essential electromechanical dynamics required for stability analysis. Um, the This diagram on the left hand side also illustrate multiple generators connected through transient reactances to the transient transmission network and loads, which are represented as an equivalent reduced network during the analysis process. So this slide present the final form of the reduced power system model after eliminating the non-generator buses from the network equations. So let me add. The original transmission network and load buses are replaced by the reduced admittance matrix, this matrix, which directly connect the internal voltages of the generators to their injected current. Since transient stability analysis primarily focuses on the rotor angle dynamics, it means the delta. Uh, sorry, let me. Uh, so this is depending on the delta. This reduction simplifies the system while retaining the essential electrical interactions among generators. So the derivation begins from the admittance matrix equations where the voltages at non-generator buses are expressed as functions of the generator internal voltages. Substituting these expressions into the generator current equation yields the compact relationship I is equal to YE. The matrix Y therefore represent the equivalent electrical coupling between generators after the network reduction process. This figure on the left hand side illustrates multiple synchronous generators connected directly to the reduced equivalent network, emphasizing that the detailed transmission network has been mathematically condensed to a simpler representation suitable for efficient dynamic and transient stability simulations. So this slide describes the admittance matrices used in transient stability analysis under different network conditions. The pre-fault admittance matrix is built using the normal system configuration with all transmission lines in service. During a solid fault on line I to J near bus I, the voltage at bus I becomes zero, so bus I is effectively connected to the ground. In the faulted admittance matrix, row and column I are removed and the connected line admittances become shunt admittances to ground. So after the fault is clear, the post-fault admittance matrix can be formed by removing the faulted line I to J from the original network. So this matrix are essential for analyzing system dynamic before, during, and after faults. Okay, this slide presents the formulation of the reduced power system using the bus admittance matrix. The current injection at each bus is expressed as a function of the reduced admittance matrix and bus voltages, where both conductance and susceptance components are explicitly expressed. By substituting the complex voltage and current relationships, the electrical power injected at bus I can be derived from the real part of the complex power expression. The final equation clearly separates the self-admittance term and the mutual coupling terms between buses, highlighting how active power depends on voltage magnitudes, network parameters, and the, the phase angle differences between the buses. So this formulation is fundamental for power flow analysis and provide the basics for understanding how power is distributed across an interconnected systems. Okay, this slide introduces the dynamic equations governing a multi-machine power system. For each generator, the rotor angle dynamics are described by the difference between the machine angular speed and the synchronous speed, indicating how the rotor position evolves over time. So the second equations, this one, represent the swing equations as we discussed before, where the rate of change of angular speed depends on the imbalance, imbalance between mechanical input power and electrical output power scaled by the machine inertia. So the electrical power expression is then substitute from the network model showing its dependence on voltage magnitude, admittance parameters, and rotor angle differences between machines. So together, these equations form the foundation for transient stability analysis, capturing how generators interact dynamically through the network during disturbances. So this slide outlines the numerical procedure for integrating the multi-machine system differential equations using a time stepping approach. The process begins by initializing the simulation at t is equal to 0. This is similar to the flowchart, you know. So where all generator speeds are set equal to the synchronous speed and the initial rotor angles are calculated from the power flow solution. The simulation then advances in a small time step delta t, updating time iteratively until the end of the simulation period is can be reached. So at each step, the electrical power output of each generator can be computed based on the most recent rotor angle values. So the network conditions are adjusted depending on the system states. So pre-fault or during the fault and post-fault, each using the corresponding admittance matrix. This allows the model to capture the impact of disturbances on system dynamics. So finally, the generator speed and rotor angle can be updated using Euler's method, providing a simple numerical integration techniques. Okay. Finally, and this iterative loop continues forming the basic for time domain simulation in transient stability studies. So this slide presents a practical multi-machine power system example used for transient stability analysis. The system consists of three generators, as you can see in the figure, each represented by an internal voltage behind a transient reactance connected through transmission reactances to a common network. The buses are interconnected to supply loads, and a disturbance is illustrated by a fault occurring near one of the load buses. This figure highlights how generator internal voltages, network reactances, and load connections form an interconnected system where disturbances can propagate. During the fault, the network configuration changes significantly, affecting power transfer and generator dynamics. All right. Um, this example served as a basic for applying the previously developed swing equations and numerical integration method to study how rotor angle and speeds evolve and to assess whether the system remains stable or loses synchronism following the disturbances. Okay. In this slide, I want to analyze the dynamic response of power system during the transient fault condition. The fault occurs at t is equal to 0.1 second and uh, is clear at t 0.25 second. This graph illustrates the rotor angle differences with respect to generator 1, especially delta 2 minus delta 1 shown in red, and delta 3 minus delta 1 shown in color. So immediately after the fault, generators begin to accelerate unevenly due to the sudden imbalance between mechanical input power and electrical output power. As a result, the rotor angle deviations increases and oscillatory behavior appears. So the blue curve exhibits a large amplitude, indicating that generator 3 experiences greater angular displacement and stronger oscillations compared to generator 2. After the fault is clear, the system attempts to regain synchronism, and the oscillations continue with damping characteristics. This response demonstrates the transient stability behavior of the interconnected power system and highlights the importance of rapid fault clearing in maintaining system stability and preventing losses of synchronism among generators. Okay, this slide present the transient response of the power system when the fault duration is slightly increased. In this case, the fault occurs at t is equal to 0.1 second and is clear at t is equal to 0.26 second. The figure shows the rotor angle differences, delta 2 minus delta 1 in red color and delta 3 minus delta 1 in blue color. Compared with the previous case, the additional delay in clearing the fault significantly affects system stability. So although generator 2 continues to oscillate within a limited range, the angular deviation of generator 3 increases continuously after the fault is clear. So the blue curve grows rapidly and exceeds 180 degree, indicating, you can see here, indicating losses of synchronism and instability in the system. So this behavior demonstrates that the system has exceeded its critical clearing time, meaning the fault was not removed quickly enough to present a stable operation. This slide highlights the strong sensitivity of transient stability to fault clearing time and emphasizes the importance of high-speed protection and circuit breaker operation in maintaining secure power system performance. Okay, this slide explains the effect of damping on the transient stability of synchronous generators. When the rotor speed deviates from synchronous speed, the magnetic flux linking the damper windings is no longer constant. As a result, currents are induced in the damper windings, producing a damping torque that opposes the rotor speed deviations. This opposing torque reduces the amplitude of oscillations and helps the system return to steady state operation more quickly after disturbances. So therefore, damping plays a critical role in improving power system stability and preventing sustainable oscillation between generators. The first equation describes the relationship between rotor angle and rotor speed. You can see where the rate of changes of the rotor angle delta I depends on the differences between the generator speed WIT and the synchronous speed W synchronous. So the second equation represents the swing equation indicating the damping term. The first part of the equation models the acceleration caused by the imbalance between mechanical power input PMI and electrical output power PEI, while the damping coefficient D introduces a torque proportional to the speed deviation. So overall, the inclusion of damping improves the dynamic performance of the system by decreasing oscillation magnitude, increasing stability margins, and helping generators maintain synchronous following faults of other disturbances. Okay, this slide demonstrates the impact of damping on the transient response of the power system following the fault. In this example, the fault is clear at t is equal to 0.25 second, and a damping coefficient of d is equal to 0.03 millisecond s minus 1. So is indicated in the system model. The graph shows the rotor angle difference delta 2 minus delta 1 in red and delta 3 minus delta 1 in blue, similar to the previous example. Compared with the undamped case, the oscillation decreases propagation with time, indicating that the damping torque effectively observes oscillatory energy from the system. So the response of generator 2 exhibits rapidly decaying oscillations, while generator 3 shows larger swings that also reduce gradually in amplitude. So unlike the previous unstable case, the rotor angles remain bonded and the generators remain synchronous through the disturbance. So this confirms that damping improves transient stability by reducing speed deviations and surprising electromechanical oscillations after the fault is clear. So this slide highlights the important role of damper windings and damping torque in practical synchronous machines by opposing rotor speed variations. Damping enhances system stability margins, accelerates the return to steady state operation, and reduces the risk of instability following severe disturbances in the power networks. Okay, this is the last slide. This slide introduces the concept of detailed dynamic models for synchronous generators in power system stability studies. In the previous analysis, the classical generator model was used where each generator is represented by a constant internal electromagnetic force or EMF behind the transient reactance. Although this simplified representation is very useful for understanding the basic principles of transient stability, it does not fully capture the actual electrical dynamics of synchronous machines during disturbances. So in reality, generator behavior is influenced by complex electromagnetic interactions within the rotor and stator circuits. To model these effects more accurately, detailed dynamic models include additional differential equations that describe the electrical dynamics of field windings, damper windings, excitation systems, and other machine components. So these equations are coupled with the mechanical swing equations, resulting in a much larger and more complex systems of differential equations. So the use of detailed dynamic models allows more accurate simulation of generator responses during faults, swing, switching events, and other transient conditions. So such models are very essential for modern power system analysis because they improve the accuracy of stability assessment, control design, and protection studies. So, however, the increased level of detail also leads to greater computational complexity, especially in large interconnected power systems containing many generators and control devices. Okay, thank you so much for your attention. Do you have any question?